So take a setup like this. You've got two faucets and they're able to drip water down into this pool below. And just one of them is going to send out circular waves like that. And if we have both of them on, then the drips are going to fall down to the water, the waves are going to overlap, and we're going to get some kind of interference. Destructive interference along these bands right here, and constructive interference everywhere else. It's a classical picture of wave interference that we've seen plenty of times before. So now let's compare that picture to the one that we have here. We have a bunch of atoms that are set up right here, and they have some separation between them, and they each have their own atomic radius. This lattice structure could be thought of as some kind of solid metal, like I think nickel is the example that they use in this experiment. And so with this setup right here, we've zoomed in to look at the individual atoms, and we're now going to fire this electron gun at them. So we're just going to send a burst of electrons up towards this setup. And when we do that, we get a pattern on the other side that looks very familiar to us. We sent these particles in, these electrons in, they hit that material and bounce back, and when they bounce back, we get an interference pattern just like we did with the water waves in the previous setup. And this experiment, the Davison-Germer experiment, was in the 1920s, and it was the evidence that we needed to prove the other side of particle-wave duality. So you have light, which is obviously a wave, but is also obviously a particle based on things like the photoelectric effect and the Compton effect. And then you've got electrons, which are very obviously a particle, but also very obviously a wave because of this setup right here, the Davison-Germer experiment. And this is the part of the story where Debroglie comes in. He put together this thesis, this idea that all matter is made up of particles, and so all matter has to exhibit wave properties as well. It's not just that the tiny things have this weird phenomenon where they sometimes are like waves. Every particle has some wave-like property. Every wave has some particle-like property, and because our macroscopic world is made up of those particles, our macroscopic world should have wave properties as well. And so this is the formula that Debroglie came up with. So you've got lambda here, which in this case is our Debroglie wavelength. You've got h, that constant we all know and love at this point, Planck's constant, 6.63 times 10 to the negative 34 joule seconds. And that one's our primary one here because usually you're going to get your mass and your velocity in terms of your standard SI units. So mass in kilograms and velocities in meters per second. And so that's why it's a better idea to use the other value for Planck's constant right here because it'll allow your units to work out nicely. So let's see what Debroglie's talking about. Let's try to calculate two special cases for this wavelength. Let's do one for something macroscopic, like a baseball moving with some velocity, and then let's do one for an electron, something much more microscopic, and see how those wavelengths actually compare. I built a table in Excel to compare these values. I've got Planck's constant quoted at the top, and I've got my information for the baseball. It's going to have a mass of 0.2 kilograms and a speed of 15 meters per second. And then I've got the electron stuff, the electron's mass, and I gave it the same speed just so we could compare those two values. And so if I want to calculate the Debroglie wavelength, it's just h divided by mv, h divided by our momentum, if you're thinking about it classically. So m times v is going to give us this tiny wavelength over here, 2.2 times 10 to the negative 34 meters. It's going to be very difficult to measure a peak-to-peak distance that's that small. But the electron, if we plug this in, h divided by m times v, we find that this is 4.85 times 10 to the negative 5th meters, or about 49 micrometers. And that's absolutely measurable. We were able to measure to the micrometer scale in our first lab. So this is more evidence that you've got this wave-like nature for your particles. The electron has a noticeable wavelength. It's got something on the scale that we can totally measure. And the baseball has a wavelength. It's just so small that we can't really perceive it. And that should make some sense, because if you were to throw the baseball travels along that straight line. It doesn't have some kind of wave nature to it as it goes along. And this is what's known as the correspondence principle. All these formulas that we're going to be building up in our modern physics unit, in our quantum physics unit, they work for the small scale, but they also have to work for the large scale. And so there's got to be some correspondence between those two scales. The formulas have to work for really, really small things, and the same formula has to work for really, really big things. In this case, the Debroglie wavelength absolutely does. It gives us a wavelength for the electrons that corresponds to our experiments, and it gives us a wavelength for the baseball that corresponds with our experiments. Namely, we don't see that it has one at all, whereas for the electrons, we absolutely see that it has one. So that's what's known as the correspondence principle. So let's look at our hydrogen atom again. This is the Bohr model for the hydrogen atom, which just has these different shells. We've seen this before. But one thing you may not know is that the Bohr model actually doesn't work so great as you go further down the periodic table. As you have more and more and more electrons, this model doesn't really work so great. The better model is to not think of these electrons as particles, but to think about them as waves. And that's the Debroglie model for the atom, which instead of having a little dot that orbits around, we have this standing wave that moves between a ring that's down and a ring that's up. And so because it alternates between up and down, this is like one wave that is sitting right here. And if we send in our photons and this electron eventually gets some more energy, it can be promoted up to one of those higher shells. And when it gets promoted up to one of those higher shells, we'll have a different standing wave pattern. Now we can see that we have multiple crests and troughs that are in there, and eventually it falls back down again. And so if I speed this up a little bit so we can see more of the patterns, this is what the Debroglie model is really doing for us. It's treating the electron as a wave, and as the wave gets promoted to higher orbital shells, that just means we're fitting more wavelengths into our setup. If we're fitting more wavelengths into our setup, the wavelengths are decreasing, and that means the frequency is increasing, just like we'd expect with E equals HF. So this is the Debroglie model for the wave. It is a slightly better model than the Bohr model, but still not exactly perfect. So at this point, we are knee-deep in this study on quantum mechanics. And quantum mechanics is a study of interactions between matter and energy at the atomic scale. So we've covered classical mechanics at the beginning of this year, and that was the study of energy and matter at a more macroscopic scale. Quantum mechanics is really the same kind of idea, just with tiny things. And these quantum formulas that we're dealing with, they have to work with that correspondence principle, that rule that if it works at the small scale, it has to work at the large scale as well. Which brings us to this nasty formula right down here, which you definitely do not need to know, but this is Schrodinger's formula. And Schrodinger's formula has a lot of complicated math in there, but it's basically talking about this thing called the wave function. And the wave function is just a function that describes the wave properties of your matter. Because matter has to be thought of as a wave, it has this function right here that treats it as such. And what we usually deal with from Schrodinger's formula is psi, that trident-looking thing, squared. And that's the probability of finding something at a specific position and time. And that is really the key for our quantum discussions. We can't say anything for certain. We're dealing with probabilities. It is most likely to be here or there, but we're not exactly certain. And that's what we've been building up to with our movement from the Bohr model to the de Broglie model, and now to our best model, the Schrodinger model. The math that comes out of Schrodinger's formula is all about probabilities. That formula is just telling you that your idea of something's position at a certain time isn't known for certain, it's known off of some probability. And this is the big divide that scientists had as quantum mechanics was coming into play. In fact, there was a giant debate between Niels Bohr, who had this model, and Albert Einstein, who is regarded as generally one of the smartest people to have ever lived. And they didn't agree. Einstein did not like at all the idea that quantum mechanics made things probabilistic. He wanted things to be deterministic. He wanted them to be, if you give me a set of initial conditions, I know where the outcome is going to bring us for certain. It doesn't really work that way with quantum mechanics. Einstein thought that meant that this whole setup just wasn't quite done yet. We needed to think about it a little bit more. When in reality, this is just the case that we have to live with. The quantum scale is all about probability, and nothing is really known for certain. And if you'd like, that's one of the reasons why the Bohr model doesn't actually work so great, because this is treating the electron as a definitive particle that's sitting at some place at some time, and you could figure that out just by using your old classical formulas. And even the de Broglie model, which is a little bit better, you still have a good idea of where that electron should be. It's just now treating it as a wave. The best model that we have is the Schrodinger model, which doesn't treat it as a particle or as a wave. It kind of just treats it as a probability distribution. And so these lights that we're showing right here is the probability of finding an electron there. It could be in this cloud that's around the nucleus at the ground state, but as it gets hit by something else, the cloud changes and it's more likely to find it in other places. So the Schrodinger model is the best one that we have, and it doesn't really treat it as a particle or as a wave. It treats it as a sum of the two by calling it just a probability distribution. We know that it is probably going to be in one of these general areas. This opens up a really interesting discussion on how things are measured, though, because classically, if we weren't certain about something, if we didn't really know our answer very well, you just make a better measuring device and you add more sig figs to your measurement. If we didn't really know where something was at a certain time, you just get a better stopwatch and then you'd have a better idea of its position at some time. But you can't really do that at the quantum scale. The mere act of measuring this thing changes the setup of the experiment. We saw that with the particle-wave duality. If you try to change your experiment to look at it as a particle, you get a particle. If you try to look at it as a wave, you get a wave. And furthermore, if you want to look at, say, some electron, specifically at that one electron, the only way you see anything is light hitting it and bouncing back. But if we have these photons of light that are hitting that electron and coming back to us, there's a collision that's occurred that could send the electron out somewhere else, and so now we once again don't really know anything about the electron. I mean, that should be frustrating. Think about these two analogies. Say you've got a fly that's buzzing around inside your room. If the fly is moving around, you could set up an experiment to measure out how fast that fly is going. You could see, where it is at one point and where it is at another point and time the distance between, and you'd know the velocity. But at any point inside that band where you're measuring the velocity, you don't really have a good measure of its position. And similarly, if you want to make a better measure of its position, the best way you're going to do that is for this fly to stop, and then it doesn't really have a velocity that you're able to measure anymore because it's not moving. So there's this trade-off. If you want to know its position, you don't really know so much about its velocity, and if you want to know its velocity, you don't really know so much about its position. And it's even worse at the quantum scale. Say you've got this experiment, this crazy, bizarre experiment, where you've got the gymnasium at the high school, and it's all locked down and dark right now because we're not allowed in the building. And say the experiment is, there is a marble that's in the gym, and you got to find it when there's no lights on and no ability to see. And it's just this tiny particle that's sitting in there. The naive way to go about it would be to just crawl around on your hands and knees and move your hands about to try to find that marble. But as soon as you find the marble, by sweeping your hand, you've now knocked the marble off somewhere else. And so that's a really good analogy of the quantum scale. The mere act of measuring things has now changed your whole setup. And you've moved the electron, and now you don't really have a good idea of where it is anymore. And this is the frustration with measurement that Werner Heisenberg brought up with the Heisenberg uncertainty principle, which looked like this. And it says, your uncertainty in your position times your uncertainty in your momentum is always going to be greater than or equal to h bar over 2. H bar we can think of as our usual Planck's constant. It is just Planck's constant divided by 2 pi. And there's another way to look at Heisenberg's uncertainty principle. You don't have to do it with position and momentum. You can do it with energy and time, where again, your energy uncertainty times your time uncertainty is going to be greater than or equal to h bar over 2. And so that h bar value I've given to you, the reduced Planck's constant, is just 1.05 times 10 to the negative 34. Again, it's just our regular Planck's constant divided by 2 pi. Let's try out Heisenberg's formula. Let's try to figure out what the uncertainty in position would be for the baseball case, and then we'll do the same thing with the electron as well and see how those uncertainties actually compare. And so all we're using is delta x times delta p is always greater than or equal to h bar over 2. I've quoted h bar over 2 up top, and let's say that we have a 0.15 kilogram baseball that we've thrown at 42 meters per second, and the radar gun that we're using to measure that velocity has an uncertainty of about 10%, so it could be 10% bigger or 10% smaller. First thing that we want to do is find this momentum, and classically that's just m times v. So we'll just do m times v, and we'll find that the momentum is 6.3 kilogram meters per second. But because our velocity had some uncertainty to it, our momentum has to have uncertainty to it as well. In fact, our momentum is going to have the same uncertainty as that velocity. Technically, we should be factoring in the mass's uncertainty as well, but we're only given an uncertainty for velocity, so we'll just multiply that by 10%. And so we know that our momentum is 6.3 plus or minus 0.63. So it could be 0.63 bigger or 0.63 smaller. And now if we want to find the uncertainty in our position, we're just going to have to solve for delta x in Heisenberg's formula. So it's going to be h bar over 2 divided by the uncertainty for that momentum. And we have a really certain value for our position, which should make some sense. Because in our classical experiments with a large baseball object, you throw it, and if you know its momentum, you got a pretty good idea of where its position is. Even if you're not entirely sure, you could make a really good guess. And what we find is that the best that you could do is 8.33 times 10 to the negative 35 as your percent error. Let's see how that compares to the electron, though. What we found with the baseball is that the uncertainty in position is really, really small, as we'd expect. You shouldn't have too difficult of a time measuring the baseball that's thrown at 42 meters per second. But let's say we have an electron, and that electron's traveling at 42 meters per second, and we are somehow able to know that its speed is 42 plus or minus 10. Well, let's find the momentum this time. And what we can hopefully imagine before even calculating is that this should be a much smaller number because the mass is a lot smaller. And indeed it is. And so then if we find that uncertainty in momentum, it's still going to be our 10% times our momentum. And now we've got a very small uncertainty in our momentum. What that implies is that the uncertainty in position should then be fairly big. And so if we do h bar over 2 divided by that uncertainty, as we'd expect, this is a fairly large number, 1.37 times 10 to the negative 5, or about 14 micrometers. And for the electron, 14 micrometers is huge. If you've got an electron and you want to know its position, and it's somewhere within plus or minus 14 micrometers, that's a huge problem for your experiment, because that band is many, many, many times bigger than the electron actually is. And so, again, this is another showing up of the correspondence principle. For the baseball, this Heisenberg uncertainty principle doesn't really do too much. For the electron, the Heisenberg uncertainty principle absolutely could ruin an experiment, because as your uncertainty in position goes up, your uncertainty in momentum goes down, and vice versa. But because they're constantly fighting each other, if you know one really well, you can't know the other really well. And if you try to do a balancing act, it really just means that you don't know either one very well. So this is called Heisenberg's uncertainty principle, and it's a way to relate the uncertainty in different values that you measure. And so again, this was the debate that Einstein and Niels Bohr had. It's this idea of whether our laws that we've built up with physics are deterministic or probabilistic. If they're deterministic, that means you get some set of initial conditions, you plug them into your formula, and you have an exact answer at the end. If you give me the mass and the velocity of that baseball, I'll tell you where it ends up. But in our quantum world, it doesn't really work like that. Quantum mechanics says that if I give you some initial conditions, you can tell me probably where this thing is going to be, but nothing for certain. And the amount of uncertainty you have is based off of Heisenberg's uncertainty principle. And so quantum mechanics kind of brings up a lot of weird things where, because nothing is said for certain, there's a certain probability that odd things could happen. In the classical world, you throw a ball at the wall, it's always going to bounce right back. In the quantum world, if you fire an electron at the wall, most likely it's going to bounce back, but there's some probability that it could just pass right through the wall. It's a non-zero value because Heisenberg's uncertainty principle, there really isn't a way to get this to work out to be exactly zero. And so this is, again, one of the oddities of quantum mechanics. We're dealing with probabilities. And because we're dealing with probabilities, there's some small chance that weird things could happen, like this quantum tunneling that we just talked about, the electron being fired at the wall and phasing right through. There are also a whole bunch of thought experiments that come with quantum mechanics, like Schrodinger's cat would be another one that you've heard of. And it's this idea that we have to really think of things with duality and with probability. The Schrodinger's cat experiment, of course, is the cat in the box, and there's some radioactive sample that has a random chance of being released, and the cat inside the box will succumb to the radiation if that random event occurs. And if you're outside the box watching this experiment and you can't see into the box, you can't really say if the cat is alive or dead until you open up the box. And so the mere act of taking that measurement has to force that system to decide whether the cat is alive or dead. Prior to that, you can't make any assumptions about what's going on in the box, and so there is this superposition where the cat is both alive or dead, based on the probability that that random event will happen. So, really odd result, and you can see why Einstein probably wouldn't have liked this, because everything that we've talked about up to this point through physics has been deterministic. I give you some initial conditions, you put it into the formula, and you give me an answer. For quantum mechanics, everything's a little bit more wishy-washy. Speaking of Einstein, though, he's going to be the subject of our next video as we move on to Einstein's famous equation, and we'll continue on from there. So, see you tomorrow.